in physics.
Yes.
I agree with that one.
Pay attention.
That was
I
agreed
disagree.
upon.
Oh,
Shh,
magnetism.
I'm recording, by the way. Chapter 19, we're going to talk about magnetism. I got to start over because you guys were talking. You don't have to write this down. You have access to this in your Google Drive. I just want you to pay attention. I'm going to record the homework problems after I go through this and post them on YouTube later tonight. 18 is posted already.
Thank you.
Okay?
I already did it.
I did them too.
Shh. All right. Starting now. Be quiet. (19.1) we're going to talk about magnets and magnetic poles and then magnetic fields. And so magnets are a lot like a positive and negative charge, and there's a magnetic field which is very similar to an electric field. The two are related. And so we're just going to talk about magnets in chapter 19, and then on 20 and 21 we'll show how the two are connected a little more in depth. But anyways, magnets have two distinct poles. There's a north and a south pole, and they usually oppose each other. Just like electricity and charges, like poles repel and unlike poles attract. And so you could almost think of this as like being a positive charge and this being like a negative charge. And so the two magnetic poles of opposite kind form a magnetic dipole. All known magnets are dipoles. In other words, they should have a north and south pole. Magnetic monopoles could exist, but have never been observed in nature. So, I mean, we could make one, but that's not how magnets work in nature. So, a magnet creates a magnetic field very similar to the electric field. The direction of the magnetic field at any location is the direction that the north pole of the compass would point if placed at that location. And so we'll get some pictures that explain that. North magnetic poles are attracted to south magnetic poles, so the magnetic field points from north poles to south poles, just like in an electric field points away from the positive charge towards the negative charge. The magnetic field may be represented by magnetic field lines. And so the closer together or denser the magnetic field lines, the stronger the magnetic field. At any location, the direction of the magnetic field is tangent to the field line, or equivalently, the way the north end of the compass points. So a magnetic field can exert a force on a moving charged particle. So we have an image here. Here's the north pole of the magnet. Here's the south pole. As you can see, the magnetic field emanates from the north pole and travels down to the south pole. And then if we pass a charged particle through that magnetic field, it causes or changes or forces the charged particle to move in a different path. So remember that a charged particle will want to move in a straight line unless another force acts upon it. This magnetic field actually exerts a force. The relationship between the magnitude of the force is proportional to the charge and the speed. So the magnetic field B, this is a magnetic field here. The magnetic field B is equal to the force over the charge times the velocity of the charge. The unit for a magnetic field is Tesla, okay? And that's named after Tesla. Now, it is possible to have an angle between two fields, so you can calculate the force by taking the charge of the particle times the velocity of the particle times the magnitude of the magnetic field times sine of theta. So sometimes the force is perpendicular to both the, sometimes the magnetic field and the force applied, there may be an angle between them, and that will be theta. We'll do a couple of homework problems on that, and that'll make more sense when we get to those homework problems. But the force is always perpendicular to both the velocity and to the field. So that's why there's a curling motion. So we are going to use the right-hand rule to give us the direction of the force. Remember that these things that we're talking about are vectors, and mathematically what we're doing is a vector cross product. We use the right-hand rule to determine the direction of that force. So while we have formulas that will give us quantities or values or numbers, technically magnitudes, we use the right-hand rule to help us determine the direction of the force. So in this particular case, if I know and I use my fingers, my index finger, to point in the direction of the velocity of the charged particle, and I use my second finger to point in the direction of the magnetic field, where my thumb is where the force is going to be exerted. In other words, the force is tangential to the velocity and also tangential to the magnetic field. A common example of an application of magnetic fields and their impact on charged particles is the old cathode ray tube or the old picture tube TVs. The way this works is that you have a cathode here, all right, and what will happen is an electron will fire from the cathode towards the anode, and then you have a horizontal deflecting coil, which is really a magnet. We'll learn in a couple slides from here that when you pump electricity through a coil, you could create a magnetic field. And then you have a vertical coil that deflects the electron. So we're altering the path of the electron both horizontally and vertically. And what it does is it'll put the electron here, put an electron here, put an electron here, and it does it really fast. And so that's how you see the old picture tube TVs. Okay, any questions? So then a velocity selector consists of an electric and magnetic field at right angles to each other. Ions entering the selector will experience an electric force. Remember that an electric force is equal to the charge of the particle times the magnitude of the electric field. And the magnetic force is calculated in a similar fashion. It's going to be the charge of the particle times the velocity of the particle times the magnetic field. The x's indicate, for example, here's the velocity of the particle going in this direction. It's perpendicular to the electric field, okay? And then the magnetic field we can't see because it's going straight into the board. So it's kind of hard to mirror or demonstrate a 3D model on a 2D slide. So if you can imagine right here where this X is, there's a magnetic field going into the page, okay? These two forces will be perpendicular to each other. Again, we would use the right-hand rule to help us determine the orientation of the various forces or vectors. Charged particles and magnetic fields can also be, we could determine their velocities based on this particular formula. So the given values of the electric and magnetic fields can be plugged in here, and there will be a single velocity that will allow ions to pass through the selector undeflected. So there is a speed that it could go so fast that the deflector doesn't have a lot of impact on it. And that will be the formula here. Remember that B is always equal to the magnetic field, D is distance, and we have V and then the velocity there. So then a mass spectrometer can be used in a similar fashion, and it can measure the masses of ions. So if you've ever heard of mass spectrometry, a mass spectrometer to determine the elements that are in something or the atoms of something, basically what they do is they fire electrons through slits, and it alters the path of the electron, and then algebraically they go in and you could calculate the mass. Based on the different atomic masses, you could determine what the substance is. They also do the same thing with light, which is why we have that spectrometer thing in there. But after passing through the velocity selector, ions in a magnetic field, they will move in a radius of a circle because of the right-hand thumb rule. These objects tend to have a circular motion, as you'll see in a second. So that radius is equal to the mass of the object times the velocity of the object all over the charge of the particle times the magnetic field. So this is what the picture looks like. Here we have a charged particle that passes through a slit. There's a double slit. There's a slit here and a slit here, and all that really does is kind of help line up the particle so that it'll go through the velocity selector tangential to the electric fields and tangential to the magnetic fields, and then it'll pass through another slit. The magnetic field here is pointing into the board. On this side of the slit, it is pointing out of the board. That creates a circular path for the particle, and then it can be picked up by the detector. The detector will measure the radius, and then we kind of use a couple of different formulas, but basically force is equal to mass times acceleration. So by plugging in some formulas for force and for acceleration, we solve for mass, and mass can be determined by plugging this stuff into this formula. So the magnetic force on a current carrying wire is a consequence of the forces on the charges. And we'll talk about this in a couple of slides. All electrons have spin up or spin down, which is kind of like a magnetic charge, which is why there's this relationship between electricity and magnetism. In most matter that like your desktop or your pencils or any matter, most of the time those electrons will travel in pairs where there'll be a spin up or a spin down, and this occurs also in subatomic particles. But basically, when we force those electrons to move, we're forcing a magnetic field to move, and we can generate a magnetic field. So the force, or what we call a magnetic force, can be generated by pumping current through a wire. So here we have the current that's going through the wire in this direction. It causes electrons to move. That generates a charge. The charge is moving at a velocity, and so all of those things are moving along with the current. There is a force that's generated that points away from the current, and then we can measure or quantify that force by taking the current times the length of the current times the magnetic field, and then sine of theta, where theta is the angle between the current and the magnetic field. So the magnetic field may or may not always be lined up perfectly with the path of the current. So an example, and then to determine where all this stuff goes, again, because it's a vector cross product, we would use the right-hand rule to determine the direction of the vectors. So basically you have a current that goes through a magnetic field. So this is the current, this is the magnetic field, this is the force. The right-hand rule is simple. Your fingers go in the direction of the current, you curl towards the magnetic field, and the force is in the direction of your thumb. Well, that force, if put on a rotating axis, will actually continue to spin something. So a current loop in a magnetic field will experience a torque. Now, torque is a force that's applied over circular motion. So the Greek letter tau, which is this thing here, always stands for torque force, which is like a rotational force. And so that is equal to AIB sine of theta. And then as you can see, we have a better picture down here. So this would be theta, okay? And then theta is the same thing here. The current enters in through the loop, but it kind of circles around the loop. And so based on the right-hand thumb rule, as the current passes this way, the force goes in this direction. When the current passes back down around through here, the force is applied downward. There's also a force that occurs here, and that's the axis of rotation. The magnetic field obviously goes from north to south pole. Now, if there are multiple loops in a coil, we just simply tack on this end that represents the number of loops, and that increases the or magnifies. It's a scalar multiplier of the torque. So the magnetic moment, which is something that's kind of important, can be determined by multiplying NIA. So then, galvanometer has a coil in a magnetic field. When current flows through the coil, the deflection is proportional to the current. So what happens is when we use these devices, and if you look in your chapter 18 homework from last night, the galvanometer is actually used, or could be used, to make a voltmeter and an ammeter. Now, Mr. Adams' fancy multimeter has all this sort of stuff on a circuit board, and it just switches. I'll show that to you guys later. But basically what happens is as the current flows through the coil, it will have a force that causes this whole thing to turn, and then it'll measure current. Basically, it's ammeter. So then electric motor kind of works on the same principle, except if you have a brush motor, we apply a current through some sort of power supply, and you have the positive contact brush here and a negative contact brush here. As this rotates, the current always enters in this way and flows out this way, which has a force based on the right-hand rule going up here and going down here. As it rotates, then the currents will continue that electrical path. So what it looks like is the force is here, it spins around this way, from there it keeps spinning, and then it'll keep on spinning. Then the forces change because the current changes. Does that make sense? Okay, so that's how an electric motor works. Sometimes you'll hear us talk about brushless motors. It's a similar process, but the way that they use more magnets and to avoid contact. So we lose a little bit of energy because it literally looks like a paintbrush of like thin wires that rubs against the contact in some cases. So you'll lose a little energy there due to friction. So some motors are brushless motors, and those are a little bit different. For now, we're going to focus on a motor with a brush. So an electronic balance uses magnetic force to balance unknown masses. The amount of the current required is proportional to the mass. So if I put a mass here on a balance, there's a fulcrum type device. So when this goes down, this knife edge comes up, there's an electric eye here. We basically amplify that signal, and it's connected to coils inside of a magnet, and we can measure that change in current, and then that's proportional to the mass. And so by doing some fancy math, we can figure out the mass of an object. So here's where we start to talk about the connection between electricity and magnetic fields. Here we have a simple power supply or battery hooked up to electric coils. And what we find is that when I close the circuit, as the current goes through the coils, it creates a magnetic field. That magnetic field changes the orientation of the compass. So right now, with the battery open, and if I have a compass that's facing north, then it'll face north, obviously. But then once I close the loop, I generate a magnetic field that's closer, and it changes or alters the compass's needle. Okay, so what does that mean? That means that the magnitude of the field can be calculated by the following equation. The magnetic field B is equal to mu naught I all over 2 pi d, where mu naught is called the permeability of free space. I was talking about this with a student. It's weird. They tell you that this is a constant that never changes, and then they give you this formula, and the question was posed, why don't they just put this in the formula? It's just easier. A lot of times when you write a program, or like on Mr. Adams' fancy calculator that I have at home, I just plug this in and I have this particular character programmed into this value. So anytime I want to calculate it, I just plug in the notation or the variable versus the actual value. So then this is what it looks like. If I point, or if I take a straight wire and I pump a current through it, and the current is flowing in this direction, and I set a compass next to it, it will align with the electric field, pointing towards or in the direction of the electric field. Now, because the current is constantly moving up and it exerts a force, so everybody take their thumb out and point it in the direction of the current. So if I have a wire that's going up and the current is flowing up, curl your fingers like this. That is the direction of the magnetic field. And so what we do is whenever we pump electricity through a wire, it generates a magnetic field that kind of rotates around that wire. You'll hear Mr. Adams talk about a Faraday cage or an electronic cage. Sometimes you ever gone in a building where your cell phones don't work right? Your cell phones operate on electromagnetic radiation. which is a pretty broad spectrum, but it's anywhere from TV, cell phones, any frequency, radio, HD, satellite dishes, anything that we transmit through the air is electromagnetic radiation. It's also light, so there's a very small sliver of that electromagnetic radiation that we could see. But when you pump an electromagnetic wave through a magnetic field, it screws it up. So this is why, and we know this is why if you ever watch one of those conspiracy theory movies, if you ever notice that those people will have wire cages hooked up to electric currents, and they do all their work inside of a wire cage, they're creating a lot of magnetic fields to cause interference so satellite dishes can't spy on them. Weren't expecting that. That one's free of charge. Back to magnetic fields. Well, now we're going to talk about a couple of different scenarios in which you can generate a magnetic field using an electrical current. If I create a loop like this and the current comes through like this, I will create a bunch of magnetic fields, but the overall effect of the magnetic field will go in the direction of the right-hand rule. So if I take your hands out, and if the current, and curl your hand this way, if the current is your fingers, right, that's the direction of the current, your thumb will always go in the direction of the magnetic field. Now turn your hand the other way. If the current rotates this way, then the magnetic field goes in the direction of your thumb. We could calculate this magnitude by taking that same permeable constant of free space, multiplying it by the number of loops, times the current, times 2, times the radius of the circle, okay? Or, well, the formula there, I said it wrong. But really what's going on is there are a bunch of little magnetic fields that go all the way around the loop. And notice that these magnetic fields rotate around this way, and over here these magnetic fields rotate around this way, and so it has an effect of a magnetic field that rotates this way. Does that make sense? A better picture of that is this. So a solenoid is a wire coiled into a long cylinder, and basically what happens is as the current flows through this way, it creates a lot of little circular magnetic fields, but they're all pointing or rotating in the same direction because of the right-hand thumb rule. And down here on the bottom, a similar thing takes effect. So the overall effect is a magnetic field that goes in this direction. Again, we could use the right-hand thumb rule to help us kind of determine the direction of that magnetic field. So a cool thing about atomic electrons is they have a property that's called spin. That gives them a small magnetic moment. It's almost like they're little small magnets, okay? In multi-electron atoms, electrons are usually paired with an electron of an opposite spin. So there's usually a pair of an up spin and a down spin. So this leaves no net magnetic moment. However, this is not always the case. Some atoms do have permanent magnetic moments. So what happens is they'll experience a torque in a magnetic field and they will tend to align up. So now what this means is in ferromagnetic materials, the forces between neighboring atoms are strong enough that they tend to align in clusters or domains. So this is just like, let's say this is a piece of iron that you see on the screen. Well, this might have like a miniature magnetic field that points this way. This one will have this one, this one will have this one, this one will have this one. And they're all going in different directions. So the net magnetic force or field is 0. However, if we apply a real magnet field to that, in other words, we have this ferromagnet material with a bunch of unaligned domains, and we apply a magnetic field to it. What happens is those domains will align themselves with the magnetic field, and then we'll make a magnet. So if you take like a steel pin and you rub it against the magnet, if you rub the tip of it against the magnet, you're aligning those little domains, and that's how you, if you've ever been in Boy Scouts, who in here has been in Boy Scouts and made a compass out of a needle or a small piece of metal? Well, you don't have to be in Boy Scouts if you've ever done that. This is actually what takes place at a microscopic level. Does that make sense? Okay. So when the external magnet is removed, the domains tend to stay aligned. However, if they do stay aligned, it creates a permanent magnet. This doesn't always happen, but the ferromagnetic materials that are most common are iron, nickel, and cobalt. There's some rare alloys that will also work. So ferromagnetic materials can be used to form electromagnets. Putting this material within a solenoid greatly enhances a magnetic field. If we want to calculate that, the magnetic field then can be calculated by mu times the number of loops times the current times the length, where kappa sub m is the magnetic permeability of the material for ferromagnets. Kappa sub m is typically several thousand, so mu is equal to kappa sub m times the permittivity of free space. All right, so here's what they're talking about. I put a magnet inside a solenoid. With an open switch, it doesn't really have much of a magnetic field. However, if I close the switch and put a current through it, I can create a strong magnetic field, and it'll pick up the iron filings. Sometimes it will work with the circuit when you open the circuit back up. Sometimes it will not. We'll talk about why. So it's like an electronic magnet. So some material, and basically what it boils down to is whether or not those domains stay aligned or don't stay aligned. If they stay aligned while the circuit's on, then that increases the strength of the magnetic field. But once you remove the current, some materials will just go back and the domains won't stay aligned. So a permanent magnet can lose its magnetization through impact or heating. Every ferromagnetic material has a Curie temperature, above which the thermal motion immediately destroys any magnetic alignment. So lava flows freeze a record of the Earth's magnetic field at the point where they're cooled below a Curie temperature. In this way, historical values of Earth's magnetic field may be determined. So a couple things I want to point out. The Earth's magnetic field does not necessarily line up with the geographic North and South Pole. What I mean by that is that this is the magnetic field South Pole of the Earth, and this is the geographic North Pole of the Earth. Here's the funny thing. Our compasses point due north because our magnetic field is actually pointing towards the magnetic South Pole. And it's not pointing due north. So if we look at how that kind of works, it's a little bit off. So this is like the Earth's South Pole, the magnetic South Pole, but the geographic North Pole is a little bit off. Now some compasses can compensate and make a difference and point due north. But we have GPSs now, so those are based on satellites positioned in space. Those are fairly accurate too. So anyways, charged particles can become trapped around magnetic fields. Such trapping of solar wind particles has resulted in bands of charged particles around the Earth called the Van Allen belts or the Northern Lights. So to review that, yeah, there's lots of names. But anyways, well, they're all different things. They're different things that we're talking about, but they're all products of the magnetic field. So I'm just throwing a bunch of other stuff out there. So to review, this is the important stuff that you guys need to remember for your homework. A magnetic force on a charged particle can be calculated this way. A magnetic force on a current carrying wire can be calculated this way. So if you have a homework particle, or if you have a homework problem that talks about a charged particle, you use this formula. If it talks about a current carrying wire, you would use this formula. Again, the right-hand rules will apply throughout this because electromagnetic forces are cross products of vectors, so you're always going to use the right-hand rule. Torque on a current loop, this formula right here. Magnetic field produced by a long straight wire, this thing right here, where this is the constant of the permeability of free space. The field forms circles around the wire. You, again, use the right-hand rule to determine the direction of those circles. If you have a question in your homework that talks about the center of a current loop or the magnetic field at the center, use this formula here. If it says the magnetic field at the center of a solenoid, use this formula here. Again, right-hand rules apply. Ferromagnetic materials spontaneously align into domains. The domains then align with external magnetic fields. When the external magnetic field is removed, a ferromagnet may retain its magnetism. Are there any questions?